Greetings, everyone. My name is Hernani Nascimento from the Federal University of Santa Maria in Brazil, and I would like to welcome everyone to the 7th presentation of the webinar series, Nowcasting Operations and Techniques, Perspectives for South America. This series is supported by the Nowcasting and Mesoscale Research Working Group of the World Weather Research Program of WMO, and we'd like to thank all the individuals who have registered in today's talk. This series consists of webinars that are normally broadcasted live at 18 UTC on the first Friday of each month, but this time we have exceptionally 17 UTC Monday webinar. The presentations are recorded and made publicly available in the YouTube channel of the Department of Atmospheric Sciences of the University of São Paulo. For these webinars, a number of professionals with long experience in research and operations in nowcasting of convective storms have been carefully selected to give talks. Today's guest speaker is John Cintineo from the USA. John's talk will be followed by a Q&A session, and for that, we would like to ask the audience to place your questions in the Google Meet or YouTube chat. We'll read your questions right after the presentation. And please, for those in the Google Meet session, remember to keep your microphone muted. Now, I'd like to pass the word to Rachel Albrecht, who is co-chairing this webinar presentation with me, and who will introduce the guest speaker. So Rachel, please, the microphone is yours.
Hi, it's my pleasure to present today's speaker, John Cintineo. So John received his bachelor's degree in atmospheric sciences from Cornell University and his master's degree in meteorology from University of Oklahoma. Since graduating from Oklahoma in 2011, he has been with the Cooperative Institute for Meteorological Satellite Studies at the University of Wisconsin in Madison. He has been the primary developer of ProbSevere portfolio models, so some of which are in widespread use by NOAA National Weather Service. And he has also been involved in research regarding volcanic ash cloud detection and diagnosis using satellite data. So his talk today will address ProbSevere products. So John, thank you for accepting our invitation to this series of webinars, and thank you for changing the date due to the World Cup that we were following here in South America. And congratulations to Argentina that won past Sunday the World Cup. So the floor is yours, John.
Yeah, thank you so much. I'm honored to be invited to this seminar series and present in this forum to you all. Yeah, eager to have a good discussion and share about some things we've been doing at University of Wisconsin over the last, I guess it's a decade now, and really appreciate the opportunity again. And I'll go ahead and get started. I'd like to thank my colleagues and co-authors, Mike Pavlonis of NOAA NESDIS, Justin Siegliff, and Lee Krantz of University of Wisconsin. So ProbSevere, let me explain what that is. So basically ProbSevere started as one model, machine learning model to predict the probability of severe in any given storm. But it's kind of evolved into a suite of machine learning models for nowcasting convective thunderstorm threats. And each model has a different level of maturity. I'm going to mainly focus on 3 models here. So ProbSevere version 3, it's basically the same thing as ProbSevere version 2, but more enhanced. And I'll describe exactly what it is. Something called Intense StormNet, and then another model called LightningCast, which are satellite-only models. So let's start with ProbSevere version 3, since that's kind of how this portfolio of models began. So ProbSevere, like I said, it's short for probability of severe, basically transforms data from multiple sources, including high-resolution NWP data, GOES imagery, MRMS products, and total lightning from space and from terrestrial networks, into a probability that any given thunderstorm will produce severe hail or wind or a tornado in the near future, so up to 60 minutes. So it's a very short fused nowcasting product. MRMS, for those that are unfamiliar, is multi-radar, multi-sensor products. It's basically a merged radar fields over the United States, and it uses some model data to do some blending and get some unique radar products that way. So it uses mainly the NexRad data. So we really see ProbSevere as it's designed to identify threats before severe weather strikes. And so getting that first warning out is really what it's targeted to provide guidance for. Okay, so like I said, ProbSevere fuses together radar, satellite, environmental, and lightning data to predict next hour severe weather probabilities. There are 4 different models. They are probability of any severe weather, severe hail, severe wind, and tornado. And in the United States, severe hail is defined by a hailstone with diameter of 1 inch or 25 millimeters or greater. Severe wind is a measured wind gust of 50 knots or about 26 meters per second or greater, or substantial damage to structures or trees, and a tornado. So any of those criteria would constitute severe weather as NOAA's National Weather Service defines it. So ProbSevere uses storm identification and tracking software in a multi-sensor sense. So we track storms in radar and in satellite imagery, and we share the satellite predictors and trends with the radar objects. And so we extract these features in predictors, and then ProbSevere version 3 uses something called gradient boosted decision trees as the machine learning engine to produce these probabilities. It's fairly similar to a random forest approach. I think a random forest could be tuned to do just as well. And this display on the left is it's called AWIPS. This is what National Weather Service forecasters in the US use to view data, to issue their products and warnings and things like that. So these little colored polygons, the kind of blue to pink ones that pop up, are what we produce, what ProbSevere produces. And you can kind of see the color legend here a little bit. So the pinker means it's very high probability of producing severe weather in the next hour. These yellow and red boxes that pop up are official severe thunderstorm warnings or tornado warnings, respectively, issued by the National Weather Service. So ProbSevere is really meant to be a decision aid to help forecasters issue these warnings or to make that decision to issue or not issue. And humans are still issuing all the warnings in the US. But ProbSevere is used operationally throughout the Weather Service in the lower 48 states. So let me describe the display of this a little bit. I think that's really important when you are using AI models. You need to convey this information really cleanly and quickly, especially in the nowcasting sense, when forecasters have to make really quick decisions. And this will also help with forecaster acceptance and uptake of the model, and just help them understand better what's going on. So basically what we do, we have these storm objects and we just draw contours around them, the outer edge of these storms, the objects, contoured around the radar data. So during a severe warning situation where you have severe weather imminent, forecasters are always glued to the radar data. They want to know exactly what's happening with the hydrometeors and the wind field inside the storm. So our philosophy is that we don't want to fight that. We just want to inform what they're already doing. So we do this by just having this hopefully unobtrusive display where you get a colored contour or probability, but you can still see the radar data. If a forecaster hovers over a storm with their cursor, they can see specific severe weather probabilities. So that's kind of on this first line: probability of severe, probability of hail, wind, tornado. they also get different predictor information in these bulleted lists, different radar predictors, a couple satellite predictors, and NWP, so some environmental predictors, effective shear, CAPE, etc., and GLM flash rates and ENI flash, Earth Networks flash rate, etc. So this really helps forecasters understand how, when you see a change in the probability, you can tie it back, hopefully, to changes in the constituent predictors. This really helps forecasters, I think, to unpack this black box of machine learning models, helps interpretability and understandability, and eventually usability of these data. So one thing that's kind of in beta testing right now is forecasters can click on a storm and get the recent history of the severe probabilities. Here, red is probability of tornado, blue is wind, green is hail, and orange is any severe. So I think severe trends really help forecasters decide. They can help decide to issue or not issue severe weather warning. Forecasters note that just the storm's history can inform what it's going to do in the near future. And this will also help prevent forecasters having to toggle back and forth in time in their display. So it saves time and increases efficiency that way too. So you might have noticed there's also on some storms this outer storm object contour. So this is colored by the probability of tornado and only is present when the probability of tornado exceeds some threshold, which can be user defined. So forecasters really didn't like to have two different products up, probability of severe and probability of tornado, though they issue two different products, those red and yellow polygons, for if there's a tornado warning or a severe thunderstorm warning. So in this way, we can enable forecasters to see both the severe threat, the hail or wind only threat, and the tornado threat at the same time in one display. So I think one important way that decision aids like Severe can help forecasters is perform triage in busy situations or prioritizing the threatening storms to investigate and make warning decisions. In this example here, there's a number of severe, tornadic, and non-severe storms evolving rapidly as they enter Wisconsin, and forecasters have to be able to make these decisions, and maybe Severe can or does help show them which storms to investigate further and to prioritize. So Severe version 3 has been evaluated at something called the Hazardous Weather Testbed in the United States the last 2 years. So this is where new products are evaluated, in this case for severe storm forecasting. At the end of each year, we ask forecasters a number of survey questions. In this case, I'm just showing from the last 2 years, does Severe version 3 in general increase your confidence in issuing warnings in your warning decision making, and does it increase lead time to reported severe weather for Severe in general on the left and tornado on the right, since we recognize that's kind of a different animal. So what we see is that particularly for Severe, any severe models, got really high percentage of yes responses. Yes, it's increasing forecaster confidence, and it's increasing my lead time to observe severe weather. Particularly in 2022, we were 80 or 90% of forecasters saying yes. In ProbTor, it's a little bit lower, but in a more active season in 2022, we were at 60% of forecasters were saying that, yeah, this is really helping my confidence in warning decision making, and it's increasing lead time to observe tornadoes. So even a couple minutes can be really crucial when you're trying to forecast severe weather. So forecasters are routinely using Severe to help with their warning decision making. So we have a web display for for PropSphere version 3. Version 2 is the official operational version, and hopefully version 3 will replace that soon. But you can get those data from that URL at the bottom there. Version 3 data you can get through our website here. There's a Real Earth API, and I can send some instructions on where to find documentation on that. So we only run this over the CONUS, but yeah, we think this is, maybe this is already being done in Brazil, but I think this is a really good approach to fuse data from a bunch of different sources you have available. Okay, let me move on to this model that we're calling Intense StormNet. So what this is called a convolutional neural network, and it uses images of satellite data to identify intense convection regions as a human would define something that's intense. So while that is a subjective metric, we're not forecasting anything quantitative. We think this is a better approach than identifying overshooting tops and things like above anvil cirrus plumes, since there's a lot of other patterns in imagery that also indicate intensity, and most human forecasters basically will know it when they see it, like, yes, that's an intense storm, and this deserves issuing a warning for or making some decision on. So this model relied on many thousands of human expert labels to determine, basically classify storms or images as intense or not intense. Those are our classes. The input data is from ABI and GLM, or geostationary lightning mapper. The ABI channels are the half kilometer visible, that's 0.64 micron, the red band, and the 2 kilometer IR window, that's the 10.3 micron brightness temperature images. And then from GLM, it's simply the flash extent density. Many of you are probably familiar with that. You can see it toggled on the little animation on the right. Basically, it's just the number of flashes that traverses a given GLM pixel over a set amount of time. So here it's flashes per 5 minutes. So it's a lighting density. So this can be output in a number of ways, but what we've chosen to do is to output these probability maps, and that's these contours here, where the blue is 25% probability of intense convection, cyan is 50%, and magenta is 90%. So you can see, especially the higher probabilities are really isolating the cold storm tops, overshooting top, and the really high texture that you can see in the viz. This background image is what's called sandwich imagery. It's basically just transposing the 10.3 micron brightness temperature with the red 0.64 micron reflectance in a way that's easy to see both data. And so yeah, so applications. The output from Intense StormNet is actually currently used as input into the PropSphere version 3. We think that's a good way to capitalize and exploit some of that rich spatial information in GOES and in ABI and GLM imagery. And this can also be used as a satellite-only nowcasting tool. It doesn't require radar. So it could be used over ocean or areas where you don't have radar coverage. We think this could be a really interesting way also to kind of do a reanalysis of convection during the GOES-R era. You can kind of, as you'll see, track these areas of intense convection over time really nicely. That's something we're starting to look into as well. Okay, so many of you are probably familiar with what a convolutional neural network is, or a ConvNet. I'll just give a really brief recap. So in our case here, it's a deep learning algorithm that uses images as input. So it's a two-dimensional ConvNet, and it assigns importance to features in the image. And based on those features, it can differentiate between classes. And again, in our problem, it's binary classification. There's intense convection or not intense convection. So it's a pretty simple problem. ConvNets learn, this is a really important point. I think people forget that convolutional neural networks learn salient or important spatial and multispectral features in the images. It's not just the gradients of a given channel or predictor. It's the spatial and multispectral components combined. And I really liked this quote I found. The role of the ConvNet is to reduce the images into a form which is easier to process without losing features which are critical for getting a good prediction. So a standard neural network, you could just take every pixel and make that an input feature or predictor or neuron, they call it. But what that does is it increases the number of parameters in your model by a lot. Basically makes the problem intractable unless you have a gigantic amount of data. And for very few problems do we have that. So with a ConvNet, there's the assumption that there's spatial coherence in these images, which there is. So there's a lot of redundancy from one pixel to the next. So it really reduces the number of parameters in your model while retaining features that are critical for getting that good prediction. So they're really powerful for anything that's image-based. Now on the right is just a really simple animation of what a convolution is. It's not very complicated. The red numbers here in this orange box represent the convolutional kernel, and the green is the bytes, the ones and zeros of the image. But basically, you can see the ones in these red numbers here are what it's trying to highlight. So it's this X pattern, and as you multiply that or convolve that through the image, you get these values here. So that's the output. And the higher that is, that means the more, in this case, the more X-like that part of your image is. So through the algorithm, the backpropagation algorithm, the model can learn which features are important. Maybe it's a certain gradient and multiple images, multiple channels in a certain area of your image inputs. So here is kind of a classic schematic of what this looks like. Basically, you have your input image and your convolutional windows, and then you make a bunch of what's called feature maps. So those are the convolved images or features kind of up here. Usually you put in pooling layers. It reduces the spatial resolution of your image or your feature maps at this point. And what that does, it helps the model learn important features at different spatial resolutions, and also helps learn features that are invariant to where in the image they are. You don't want the model to learn that a certain feature has to be in this part of your image. The ReLU, that's a nonlinear activation function. That's how this model can learn nonlinear features. So you have a couple blocks like this, feature learning stage, and then you flatten all of your features. So you make a vector, and then you add a couple fully connected layers usually, and you get your classifications. And for us, it's just the probability of intense convection. So this is what intense StormNet looks like. We have two different input branches, one for ABI and one for GLM. You can just put them all together. We found this worked a little bit better. We're not exactly sure why. We think maybe because the GLM just looks so much different than ABI that the features the model is able to learn is just a little bit more tailored with two branches instead of one branch. But you can see we have several blocks of convolutions and poolings, and then we flatten everything together. We add scalar features, latitude, longitude, solar zenith angle, and satellite zenith angle. We put a couple fully connected layers, and then we end up with one probability of intense convection. So for a given image patch, and in this case, you can see the horizontal dimensions. So it's 32 by 32 at 2 kilometer resolution. So that's approximately 64 kilometers by 64 kilometers. So for a given 64 kilometer by 64 kilometer image patch, you get one probability of intense convection. So it was a lot of tedious work to create this training database. I just wanted to kind of show where all these storm tracks were from. I forgot, it's over 200,000 samples that we were labeling in every 5 minutes for every storm. So you can see the eastern 2/3 to 3/4 of the United States are very well sampled. The western third or so, not so much. But yeah, you really, for a lot of problems, you need a pretty good built up database, and your models are only good as good as your truth data, or as your truth and training data are. So we wanted to make sure we could do as good a job as we could, and actually have humans go through lots of images of satellite data for storms. Okay, so I'm going to show a number of examples of intense storm net. This one, the background SAM imagery is a little bit different color map, but this is a storm on the Oklahoma-Texas border, and you'll see these contours pop up. So this is, a pretty strong storm. It's a supercell, and you can even see, as this will get going again, you can see a split, a left split on this storm, so that the model picks up on and has some higher probabilities for. So the model, because of the GLM and the channel 13 IR band, it works day and night pretty well. We can use this on the 5-minute CONA scans or the 1-minute mesoscale scans. The way it's designed currently, you can use it basically on any temporal resolution. You just need one set of images at one time frame. Despite being trained on GOES 16, the model runs pretty well on GOES East and GOES West, as long as the viewing angle isn't enormous. Like I said before, it doesn't require radar data. And we have near real-time output available at CIMSS, currently just over the contiguous United States. Okay, here's another example with the 1-minute updates. This is, before I get started, the little dots that pop up are severe hail, wind, and tornado reports. So you'll see those pop up along with the contours evolving. So this is in south central Texas. Again, this is a number of pretty strong supercells. And hopefully, as I let this move forward, you'll see that most of these areas, especially where you have 90% probability of intense convection, you're getting severe weather reported. And even as you have this huge area mass of thick ice from these anvils, the model's really just honing in on the strongest parts of these storms. And it kind of transitioned tonight at the end there, and still did a pretty good job identifying the strongest areas. So yeah, I think it showed pretty good correspondence with reported severe weather. Now, again, these are for mostly supercells, which are the most intense types of storms. But there's other types of severe weather too. So this is in the southeast US, and there's definitely some linear convective structures mixed in. Let me go ahead and play that. This was from just a couple weeks ago. And again, you'll see the reports pop up, and as this transitions to nighttime, the model is still doing a fairly good job identifying the strongest areas of all this convection. So what we've noticed, and I think you can see a little bit in this case, is that there is an underestimation of what I would call intense, where you basically have 0 or very low lightning flash rates. So when GLM is either showing nothing, or there's just so much optical extinction of the lightning signal, you need a really robust ABI signal. So really strong overshooting tops, really strong storm top texture to overcome the 0 lightning. But so a lot of times those storms just don't have lightning. They're either like really highly sheared, so you get tons of wind reports and few hail reports, or something to that effect. let me move on to the next example. So during the Relampago field experiment in 2018, 2019, 2020 maybe, there was a 1 minute sector put over Argentina several times. So we collected some data from that, and we were able to run the intense storm net on that. So this is a 1 minute sector. And I know it's a little bit zoomed out, but hopefully as this gets going, you'll be able to see that, again, it's doing a pretty good job highlighting the strongest parts of the storm. And I realize now that that color bar for the brightness temperature isn't very good, since there's some definitely much colder cloud tops than 193 Kelvin that get washed out a little bit. But I know in this case, there's some very strong storms near Cordoba, where you had 50 dBz echo top up to 20 kilometers or even higher, which is pretty remarkable. But yeah, so even in this part of the world, in Argentina, I think the model does a respectable job identifying the intense parts of the storm that did produce hail and widespread flash flooding and some wind damage. So another example I took recently, I basically just tried to identify some basically random storms in southwest Brazil, and I plotted the GLM flash extent density on the right, and then the intense convection probabilities on the left with the sandwich imagery. And I was a little surprised how high the intense convection probabilities were. To my eye, these kind of looked like more benign thunderstorms. Surely there's definitely some intense downpours, I'm sure, but I'm not confident that they're producing lots of hail or really damaging wind gusts or anything like that. I haven't had a chance to dig into why that is. It could be that some of these GLM flash rates on the right are just really high compared to what we get in the United States for more comparable looking convection. But all this just to show that, the model certainly isn't perfect. Probably has more work to be able to do to be able to perform well in other areas that wasn't trained on, like in Brazil. So another thing that we performed was a permutation test. And basically what this is in order to rank how important these predictors are in the model. So that's really important for just being able to explain your AI model. Real quick, the permutation test, basically you jumble up each predictor one by one. So you take away any correlation it has in between samples, and then you excuse me, and then you compute your whatever statistic you want. In this case, it's the area under the receiving operating characteristic, so the AUC, area under the curve. And then in successive permutation test, you jumble up the one that decreased that skill metric the most, and then you do the next, each one iteratively. So you do the top one, the top two, the top three, you keep going until you're out of predictors. But basically, we found brightness temperature decreased the skill the most when we permuted that predictor, the channel 13 brightness temperature. So, and this is for a daytime only sample. So it's the channel 2 reflectance has just as much weight or input as channel 13. And then I was surprised that the GLM flash extent density was the second leading predictor, even more than the channel 2 reflectance. So that just goes to show how important having that electrification information is in this image-based model. And then the last image input was the third most important, and the scalar inputs were less important. So there's different ways to do this permutation test, but yeah, this is a good way to really evaluate what does your model say is important. Okay, so Intense StormNet, we also have a web page for. You can get the GeoJSON data through the Real Earth API. Again, we're only currently running this over CONUS just due to hardware limitations and demand. But we could run this in other parts of the GOES 16 or 18 geo rings. Okay, let me move on to this last model I'm going to talk about, lightning cast. So what is that? This is another type of convolutional neural network that was trained to predict the probability of lightning in the next 60 minutes as defined by GLM, or as observed by GLM. So the label data are aggregated GLM flash extent density over the ensuing or next 60 minutes. And the input data is all from ABI, the red band, the 1 kilometer shortwave IR band. So that's the snow and ice band, or channel 5, I think it's 1.6 microns. And then two different IR window channels. I think they'll be on the next slide. So this, of course, has a lot of applications to protecting life and property. We can also possibly use this to study things like answer the question, well, why is one storm producing lightning and the other one isn't, or something like that. So this ConvNet is called a UNet. It's a very popular type of convolutional neural network where you get a prediction at every pixel of your image. So here are the predictors again: the 0.5 kilometer red band, 1 kilometer snow ice band, 10.3 micron brightness temperature, and 12.3 micron brightness temperature. So these first three channels constitute the day cloud phase RGB. And what that is, it's really good for visually seeing clouds that are glaciating, which we know is correlated with lightning production. And the second two channels are the split window difference, which can show not only help in evaluating cloud height, but also help you pick up on low-level moisture pooling. So like I said, the target or truth data is GLM flash extent density, basically one flash or more in the next 60 minutes. And the output is the probability of lightning at any location within the next 60 minutes at 2 kilometer spatial resolution. We found that 2 kilometers, it's a little bit noisy, so we often just reduce this to about 4 or 8 kilometer resolution. So this is basically more or less what we're trying to do: objectively quantify the day cloud phase RGB and split window difference into a probability of lightning that we can contour. So I'm going to show a few examples of this. There's a lot to look at. I'm going to point out a few things on the next slide. This is the Florida Peninsula, a lot of sea breeze convection. The background RGB is natural color RGB. I chose to use this instead of the day cloud phase distinction in this case, just because I thought it was easier to see some features. So I'll go ahead and do this. You can see the probabilities increasing. I'll let it run through a few times, but you can see the probabilities increasing in most cases before there's observed lightning. As the cube becomes more agitated and vertically growing, the probabilities are increasing. So let me go ahead and point out a few things. And I've annotated the image where we have quantified the amount of, or approximately the amount of lead time to the first flash in a bunch of these different cells. So it ranges from between 10 and 50 minutes of lead time as measured from the cyan 25% probability of lightning. So there's relatively few false alarms. And one really neat thing we found is through multiple independent lines of evidence. So through an offline study that we published on, and through two different forecaster test beds, they found that lightning cast provides 20 minutes or more of actionable lead time to the initial flash, so lightning initiation in a median sense. So 50% of the time, forecasters are finding you're getting about 20 minutes of lead time to the first flash. So we think this is a really good result for a number of applications. Users can take some action, but we do think this is a starting point. We think we can do better. with observations only, because we recognize that some users need more than 20 minutes of lead time to take action. So think about stadiums or outdoor festivals, things like that, amusement parks. Here's an example of lightningcast output with the 1-minute updates, mesoscale sector over central United States. And the background here is the day cloud phase RGB. So you can see it's a little more complicated scene. You have the some upper level and mid-level cloud, but the model can, as our eyes can, still pick out these developing queue underneath the upper level cloud debris. Not only this main area here, but some areas to the south and east and north as well, and several of those become electrified too. So you don't need just a perfectly clear sky to be able to operate the model. One interesting thing I thought I'd point out is one tool we're using to help explain the AI model is called layer-wise relevance propagation. And basically it outputs the relevance or importance of each pixel for each input channel for why the model predicted the probability that it did. So this is just zoom in on one of the time frames from the previous animation, and the pixel of interest is right in the middle. So that's what this black X denotes. And the probability at this time was 58%, you can see here. And each window on the right here shows the relevance from the LRP method for each channel. So channel 2, channel 5, channel 13, and channel 15. So the darker red means the more relevant that pixel at that channel is. So no surprise that glaciated clouds are important for predicting a high probability of lightning in the future. But we have seen some other things too. And you can see some hints of it where some nearby water clouds are also contributing to a higher probability of lightning. Basically, what we've seen in a few other cases is just the congestion of cumulus in your neighborhood is important. So I invite people to look into this package on GitHub. It's pretty easy to use. In this case, it's just showing what are the positive contributions to our prediction, and there are ways to get the what's contributing and what's detracting from your prediction as well. Here's another example off the eastern US coast, 1-minute updates, and this is nighttime only. So the Viz and near IR bands aren't being used at all. But hopefully you can see in this developing corridor of convection that the probabilities are ramp up well before you get the GLM flashes. So yeah, even at nighttime, it does a pretty good job as well. Lightningcast was evaluated at the hazardous weather testbed as well, in kind of a what's called decision support services mechanism. So this is where forecasters provide tailored, more frequent updates to emergency managers, people that just need more information. Maybe they're managing, like I said, an amusement park or a stadium or outdoor event. In this case, a storm went up between 2 outdoor music festivals, I think, and that Lightningcast was able to pick up on pretty well in advance of the initial flash. This storm would intensify rapidly and cause problems for the festival to its east in Syracuse, New York. One thing that we're working on is making a time series or meteogram capability in the forecaster's AWIPS display. We recognize the value in being able to drop your point somewhere and have a graph of how the lightning potential is evolving in time. So this would be really good for things like outdoor stadiums or events. Here's an example from Northeast Brazil. I believe this is the mouth of the Amazon here. This has 10-minute updates with the full disk data. It's a little bit zoomed out, so it might be a little hard to see, but maybe focus your I'll let it run through a few times, but you can focus your eye on one or two areas. But you can see in this, largely sea breeze type scenario that the probabilities are increasing before you get the first flashes. So I think the model is doing a good job with the lightning initiation. So we've also, we have this loose collaboration with IMPI where we're kind of sharing tools that and ideas we have for nowcasting convection. So as part of this collaboration, we did a validation of lightning cast over Brazil. We evaluated 5 days of every month. And again, our target or our truth data is next hour lightning occurrence as observed by GLM. So here's the domain, and here are the results. The top left is probability of detection, top right is false alarm ratio, and bottom left is critical success index, or CSI. And we binarized these stats at a 35% probability, so that's approximately the best performing probability threshold. But you can see for most of Brazil, the CSI is kind of between 0.4 and 0.55 or so. Pretty good probability detection, relatively low false alarm rate. Over the ocean, you do have, especially northeast of Brazil, you have a very high false alarm rate. I'll touch on that in a minute. So we compared our evaluation over Brazil versus over North America and Central America. We find that it's pretty comparable. We think the model is working about as well over Brazil as it does over North America. So we have found that critical success index really varies according to lightning climatology. So up here, where the performance is not very good, you have really a dearth of lightning flashes to begin with in general. This is probably due to a couple of factors, probably mainly just the difference between maritime and terrestrial lightning, though it was trained on lots of maritime storms as well. But also, there's a possibility that GLM detection efficiency could be affecting the performance here, where if for some reason GLM is not detecting the few flashes that there are in this region, then you can get erroneous false positives, which would lead to that high false alarm ratio. So it could be several things going on here, but in general, the model varies according to lightning climatology. And yeah, I'll just end here on my summary slide. Prosphere version 3, the gradient boosted decision trees. It's how we fuse together all these data sources to provide guidance to the U.S. Weather Service on our short-term warning decision-making. Intense StormNet, though somewhat more subjective, that it could be a really useful standalone satellite-only convective tool, nowcasting tool. It's used within Prosphere version 3. And then Lightning Cast, the UNet convolutional neural network, satellite-only lightning prediction. Because it uses the satellite data, I think it's adding lead time over radar-only metrics of prediction. And I think it really excels at lightning initiation forecasts. So hopefully that gives you a taste of what we're doing with ProvSevere and how we're applying it to different operational problems here in the U.S. So yeah, thank you all for listening, and be happy to take any questions.
All right, thanks, John. Very fascinating work, impressive results there. So I'm sure we're going to have plenty of questions. And Rachel, do you want to start, or?
Yeah, well,
okay.
We have one right here from Dominic Brunet. Thanks, John. You showed many impressive products. If you want to develop these types of products in our own country, what would you suggest to be the best way to start? I had the same question.
Yeah, I actually don't know what all is being done at MP currently, but I mean, yeah, I right? You have all of the GOES data, the GLM data. So I would just start with that and use different Python APIs for the machine learning end of it. There's some pretty easy to use ones that a lot of you are probably familiar with. scikit-learn is one, as well as TensorFlow or PyTorch for the image-based deep learning. But I made the point that you really need to start with feeding robust data into your models. If you don't have really good training data, the model's not going to learn very well. So defining the problem is really important, and then wrangling your data, getting it all in the formats you need is probably the most important. The actual training of the model, I think, is actually not that hard and doesn't take a terribly long time. And there's a lot of, it's kind of an already solved problem in that, okay, use this type of model for this, use this type of model for this. So it's really posing your problem well and collecting your data. So I don't know if that answers your question, but yeah.
Dominic, correct me if I'm wrong. I think you are from Canada, right? And like different worlds, realities.
Okay.
Yeah, go ahead. You can talk.
Yeah. I know it's a meeting for South America, so I want a question that is also applied for others, but we're neighbors, so sometimes we wish the proxy just go a bit more north because it's used, but it's
yeah,
well, work to start again, like to do the same thing again. It's a lot of work to start from scratch.
Yeah, I mean, MRMS does go into Canada, so I think it's something we can definitely extend up there. So yeah, Canada, you have that benefit. But yeah, I mean, I know that we have this database in terms of the 10 StormNet. We have this database of a lot of hand truthed labels. So that's something I think we're willing to share, and maybe folks can build a model off of that if that's the type of product that people are interested in. So yeah.
Yeah, so I think you need to expand north and south, you know. Go full disk.
Yeah, we need some stronger computers to do that, but yeah.
Okay, so I had Hernani, you can, if you have one.
There is a second question here in the chat by Caio Atila Pereira Sena. Thank you, John. Considering a small set of labeled data as a target, could you recommend some types of augmentations to apply to ABI data?
Yeah, hi, Caio. Good question. Yeah, we haven't done a whole lot with data augmentation, just because, we've been able to get pretty large data sets on unaugmented data, but I have tried just doing a small random noise, adding small amounts of random noise to your images seems to help a little bit. I think you do want to be careful when you start doing rotations and flips and things like that, because some of those, depending on how you run your model, you're just not going to see a storm that's, upside down. Right. I guess I'm thinking more northern hemisphere, especially in like the Northwest US, you get some pretty big viewing angles where if you invert that, it's just, it might not hurt, but it might not help really either. But I suppose in Brazil, I think some of those rotations and things like that might actually be helpful because you don't have very differing viewing angles. So that could help augment or boost your data set. But yeah, that's a good question.
Okay. There's another question by Rakesh Ghosh. Can you comment about the detection of severe weather in tropical region? How it would be difficult to compare to CONUS, especially the lightning detection?
Yeah, well, hopefully I was able to show a little bit of that in the South America, I think lightning detection, I think maritime lightning is just harder to predict. You get some really tall, robust-looking storms that at least GLM isn't observing lightning. And I don't know if that's because of the differences in cloud condensation nuclei or just the differences in the CAPE profiles. So I think one thing we're going to start doing is try to make a maritime only model where we just train on ocean only images, basically. Even with that, I think you might need to bring in some other data if possible to help with really boosting the skill of maritime predictions. So maybe there's some NWP information that can help a little bit there. But yeah, we have found that in the tropics, in the tropical oceans, the model definitely doesn't do as well as over land.
I have a comment on that. Like you showed those storms in Southeast Brazil on November 9th, right?
Yeah.
And you comment that you didn't know what was going on, too much lightning. And that day in particular, we had 20 hail reports.
Okay, so maybe they weren't.
Region. Yes. And mostly of them were like 1 or 2 centimeters, but we had 3 reports of large hail, 4, 6, and 7 centimeters.
Oh wow! So I just picked a bad day, or I'm a bad interpreter of visual.
No, that was unusual. It's not that common,
Yeah.
but you picked the right day. So the comment is that most of the time people underestimate our storms.
Yeah, there you go.
We can get hail.
Yeah. Is there a good database of hail reports in Brazil or South America?
We are building one.
Nice.
With our own hands. Actually, with Bruno's hands.
Well, that'll be super important, right? You need good truth data. So that's awesome.
Yeah, we have reports since 2018, mid-2018, when Bruno started.
Good. Excellent.
And this brings one question, which is my question, is that how do you, regarding the severe weather probability, how do you calibrate that? I mean, it seems to me that the algorithm is detecting storm features either from radar reflectivity or GOES satellite imagery, but then how does it calibrate the probability of having hail or tornado? Do you need to feed in to feed the model with storm reports? How does that work?
Yeah. So yeah, the severe weather models. So yeah, we use storm reports from the U.S. to train it. Calibration can be tough because all these problems are you have unbalanced data sets, and sometimes the models they want a more balanced problem. So we have to kind of do some selective sampling, but you don't want to do too much because then your calibration it gets messed up. So that calibration, what I'm referring to is the probabilities produced by the model actually match what's happening in reality. So you get 40% probability, then you should expect 4 out of 10 times that your model produces severe weather. It does seem like random forests and gradient boosted decision trees are a little more forgiving. You don't need a 50-50% split in your classes, but even like 10% severe, 90% non-severe, it still does a good job and retains a good probability calibration. But yeah, so we're just using storm reports. I know there's issues with those reports, but because we're using radar data as predictors, we didn't want to also use that as a way to define severe weather. If that makes sense.
All right. Okay.
And there is a question from Gabriel Mandanda. Thanks, John. Can you comment in detail on the methodology you used to track convective cells using convolution networks? And also, did you make any adjustments to reduce false alarms?
Yeah, that's a long answer. I'll try to be brief. Yeah, storm identification and tracking is a hazardous business because there's just, it seems like whatever method you use, there's just always some issues with it, especially splits and mergers of cells. We use something that the University of Oklahoma developed. It's called the Warning Decision Support System Integrated Information, or WIDS-2. Basically, the algorithm is enhanced watershed enhanced watershed transformer algorithm. I think there's some open source implementations of that in Python. So I'd invite you to look at that. So that works pretty well most of the time. That's why we use it. But unfortunately, I feel like there's always going to be some issues when you're dealing with imagery of this nature. In terms of making any adjustments to reduce false alarms, right? So we do get some tracking false alarms. The only adjustments we make basically because of the, let's see, what do we do? Sometimes we throw away some images that were just, because we were looking at all of them and labeling them, we can throw away some that basically were messed up because of tracking. I think that's all that we do there. There's probably more that could be done, especially for the probability of any severe type models. But right, it's just so much data to sort through. So you want to try to have as good of automated methods as possible. But yeah, I think identification and tracking, there's always going to be some artifacts, unfortunately. Good question.
And there's another question by Rakesh Ghosh. Is LLM data can be used in Lightningcast?
LLN, is that like the
I think it's lightning location network.
Yeah.
Okay.
It could be. One thing we're starting to look into is using GLM, flash extent density, at time 0 to also predict the probability of lightning in the next hour, along with the ABI channels. So one thing we want to, you'd imagine if there's, just from persistence, if there's lightning now, there's a decent chance that there's going to be lightning in the future. I think it would improve that end of nowcast. But what we want to make sure is that it doesn't hurt lightning initiation nowcasts. So that's one thing we're evaluating right now, since that's kind of the main goal of a lightning cast. I think that would definitely, lightning location information would definitely aid in the truth or target metric. So, right, GLM doesn't have perfect detection efficiency everywhere. Some of these networks can augment some of that and provide more robust targets or truth for training the data. So maybe somehow translating that LLN data to something that looks like GLM or something like that. I think that's a good idea.
Maybe using total lightning data from the ground, basically.
Yeah, like Earth networks or Vizsla. Yeah.
You mentioned, like when I comment that you should go full disk, about the computer power. Like, how much computer power do you need to run these models?
I think we could do full disk if we just break it up a little bit more. Training the model, you pretty much need GPUs, graphic processing units, or else it's just going to be way too slow. And so I know those are expensive, but you can also use them fairly cheaply on Google or Amazon, things like that. In terms of making predictions, inferencing, that's called inferencing. We don't use GPUs to do that because we want to save those for experimentation and training new models and things like that. So we just use CPUs on a server, a Linux server. basically the more CPUs, the better. But for like a CONUS wide image, you can, I think we use something like 40 CPUs, and it makes a prediction in like 15 seconds or something. So it's
not bad.
Yeah, and the CPUs don't have to be used, if they're not used 100% of the time. They'll make their prediction, then they'll be idle for a while until your next set of images come in. So for a full disk, yeah, I don't know. You probably want like over 100 CPUs, but I don't know, maybe you can get away with like 60. It's something we haven't evaluated fully, to be honest. And I'm speaking about the image-based models, the Intense StormNet and the Lightning Cast. Prob Severe is kind of a different animal. You don't need quite as many CPUs for that.
And John, when you described Lightning Cast, you showed the good performance in lead time for the initial flashes. And how about the dissipation? Do you get also good performance there?
Yeah, sometimes, not all the time. It kind of depends. Yeah, we've seen situations where the probability signal will decrease because of the warming brightness temperatures, and before there's that signal in radar, which is really encouraging. And then other situations, you just retain really strong, really cold, textured cloud tops, and there's just like no lightning. Physically, I don't know why that's happening. There's definitely convection, but it's just not. It's kind of just this mid-level meager convection, which kind of looks intense, or looks like there should be lightning, but there isn't. So both ways, it's sometimes good, sometimes not very good, and we get some false alarms.
Okay. We also have a question. This one comes from the YouTube chat from Pedro Augusto Sampaio Messias Ribeiro. Thanks, John. Very interesting. Do you think about using a terrestrial lightning detection network together with GLM Lightning Cast? I think this is related to the previous question, right?
Yeah. I think that would, like I said, enhance the truth data set. Yeah, I don't know if I'd want to use it as a predictor quite yet, but definitely enhancing the truth data set could be useful.
Okay. Rachel, any other question that you see there?
No.
Well, I'm just curious. This is more, I don't know, maybe a philosophical question. We see here all the application for, true application for forecast and nowcasting. Do you see, John, opportunities for, producing new knowledge regarding, storm features and severe weather occurrences coming from this type of approach?
Yeah, so this is it's a good question that we're more operationally minded, so we haven't delved into that a whole lot, but we have a little bit, especially with some of that stuff I was showing with the layer-wise relevance propagation. So you can illustrate like, okay, what is the model learning? What features? With the Intense StormNet, some of the features that you'd recognize as being intense, so strong overshooting tops, the cold U signature, like, okay, yeah, the model's learning what it should be. One thing with that model that we kind of found is basically really strong brightness temperature gradients were also really important. I think that kind of makes sense, looking at imagery for a long time. Basically, in my mind, it's kind of defines kind of the crispness of the anvil edge is more indicative of strong, robust updraft. So to my knowledge, it's kind of the first time that anyone's been able to quantify that like, yeah, those strong brightness temperature gradients near the core of the storm where you have the strong overshooting top are actually really important for determining what's intense convection. But I think any of these models, there's potential for more knowledge discovery and yeah, generating information that way.
Great. That's really a fascinating topic.
Yeah, thanks. I think so.
Yeah, I don't see any more questions.
Me neither.
Yeah, so thank you very much, John. It was very interesting. I liked it very much. I'm sure everybody did.
Yeah.
Thank you. Yeah, it was a pleasure. Hopefully, Rachel or somebody can share my email if anybody wants to get in touch with me. But
sure.
Yeah, it was great presenting to you all today. Thank you for having me.
Right. Thanks a lot once again.
Right.
Thanks, everyone.
Thanks, everyone.
You.
Thank you, guys. And
Okay.
yeah, have a great holidays.
And you too.
John, if you could just stay a little bit.
Sure.
Richard, did you end?
What's that?
No,
She's
I'm asking Richard if he ended the transmission.
Oh.
Sometimes he does like several transmissions at a time. I don't think so.
Well, I would guess so. That he ended.
You are all in YouTube.
Yeah.
Yet.
All right. Richard, are you there?
Maybe we can just, if we hang up the transmission and
And
I'm
then
not sure.
back?
I know, I'll just get another link here.
Oh, I see. Okay.
Just do another one. Here. Just go here.
So now the transmission in YouTube ended.
Ended. Okay, so we don't need to go back.
All right.
Okay. So, John, very nice. And we are very, very interested in getting this working here in South America.
Yeah. So,
and
I don't know if you know, so you know Kaio, he's a PhD student with MP. He works
Caio
with
Sena. This one that was here or another Caio?
No, this
Caio,
one. And I'm
Sena?
a student.
Yeah, so he's hopefully going to come visit for a 6-month stay at CIMSS, and we're going to talk about some of this work. And I think he's trying to develop something very similar. Maybe he can use our data set to work off that, or we can work together a little bit for him to make a model that'll work well in Brazil. In terms of, he's interested in hail forecasting. So hopefully sometime next year he'll be visiting.
Yeah.
Great.
But
and
yeah, in terms of like sharing the lightning cast, I don't know if there's interest there. Because it's all funded by NOAA, I think it's okay, but basically you just have to.
We can talk about it, like get MOUs and stuff like that. That's fine. We can.
Yeah, it's
probably
it's
Fluently, but which is easier than Thiago here. You are.
Yeah. We also we submitted a proposal in the. I guess it was submitted last week, and probably we're gonna have some money to spend on this project, on this, all that NOAA projects that we have discussed in the last 2 years, not only the nowcasting severe storms, but radiation and modeling and other stuff. And there's some grant money to do visits and everything that I guess it was Mike and Milton that discussed this on a more like bureaucratic level, but I'm pretty sure our grant was approved to do specifically those NOAA tasks with INPE.
Great.
Yeah, that's great. Now we have a very good database on like hail and wind tornadoes, which are like not much. Those we don't have much, but
yeah.
But yeah,
one thing I didn't mention is these models, they're only trained on a couple years of data. Like I think Lightning Cast was trained on 1 year, and PropSphere was trained on a couple years. So like you don't need a huge database, but yeah, you get 1 or 2 years, and that's a great starting point. And then obviously you can just keep building on that. So that's good to hear that you got that database going.
Yeah, we have around four years now of data, ground reports. We have had so his hail, damaging winds and tornadoes, so yeah, could work on that.
Excellent.
You don't by any chance have like, or can do like very easily like set up one for operations for a while
over Brazil, like a sector?
Yes, particular interest I'm asking because we are right now we are having Café Field Campaign, which is a German aircraft that is flying through the Amazon measuring gases and aerosols. And one of the things we are doing, we need to measure the outflow of thunderstorms to get whatever thunderstorms is like just speeding up to the troposphere, up the upper troposphere. And we do nowcast for that, for the aircraft.
Gotcha.
And it would be wonderful just to have that the probability to guide the aircraft to go on very new, fresh convection that could have lightning.
Send me an email with like where exactly you want it. If it's not too big, it's probably doable. If it's the whole country of Brazil, it might be a little harder.
No. It is the Amazon basin. We cannot go over the limits.
Yeah. No, just send me. I think that's doable. I can do some tests, but yeah, send me some basically lat long bounding box coordinates and see what we can do.
Yeah, it would be a pretty good test drive. Like we will all be there looking every day.
So you can
on that.
Evaluate it, see if it'll work for you, or if you need to, basically build your own model to more tailor.
Yeah, get that feeling if that works. And actually, within this Brazilian Nowcasting committee, we will start nowcasting in Manaus, which is like a hard place to do. But
yeah, huh?
And that
why is it so difficult to nowcast there?
Yeah, tropical convection pops up.
Yeah, just keeps going. Yeah. Okay.
Well, thank you guys.
Yeah.
You have it.
Thanks again, John. So
thank you.
Yeah. Thanks again, everyone.
Yeah. Nice to meet you all. Take care.
Nice to meet you.
Bye.
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 Ei, Thiago.
Oi.
Esse não é daquele negócio do fundo do FNDCT, sei lá o quê.
Esse é Então, isso aí foi o seguinte: a gente tinha lá no começo dessa parceria com a NOAA.
Pessoal, só para não ser mal educado, eu vou ter que sair da chamada.
Pode sair.
Tá ok, então um abraço a todos. Até mais.
Até.
No começo começo não, 2 anos atrás, teve um convite, foi um convite, umas reuniões que a gente já tem um monte de série de parcerias com a NOAA, né? Mas aí teve o Milton Chagas, que é um cara de relações internacionais do INPE lá. Eu não sei o cargo dele, mas tem uma coordenadoria de relações internacionais. Ele e eu falei Mike, mas Mike é o cara que trabalha com o John. É Eric Madsen, que é da NOAA, que é o coordenador de relações internacionais da NOAA. Eles entraram em contato e propuseram uma parceria entre o INPE e a NOAA. E aí tinha vários subgrupos, né?
Ô, Thiago, acho que ainda tá transmitindo essa porcaria. Não sei, vamos naquele. Vem aqui. Você falou que tinha parado?
Não, ele fechou, e aí só que eu apertei de novo lá, ele voltou e tá ao vivo.
Tá, não, depois ele corta. Eu tô entrando.
Alô, pessoal, depois eu corto, tá?
Sim.
Ainda estava transmitindo.
Não, mas não tem problema, depois corta.
Tá. Vocês querem que continue transmitindo essa conversa?
Não.
Tá bom,
Eu até
então.
derrubei as pessoas daí que eu tava.
Tá ok, então. Só um momentinho, então.
Eu não derrubei você porque eu não sabia se a gente ia cair.
E aí